particle theory, gases exist in a state of matter where each particle moves freely and independent of each other. Particles move in straight lines unless acted upon by some force. So, like we said, there's an uncountable number of particles, right? Like, we'll get to the number later, but every liter of gas at room temperature is about a mole. Does that make sense? So if you have a liter, so this room would be, I don't know, but we can figure out how many liters, but this room would be, 1 million liters or something like that. And so you're talking about, about 1 million moles of gas in this room, right? So, just an uncountable number of particles. And each of those particles is moving us on a straight line until it's acted upon by some force. And that force, gravity acts on it, things like that. But the main thing that acts on it is the main thing that happens is A, gas particles collide with each other. This transfers energy. So gases tend to match one another in speed. And that, of course, means that heat disperses through them. We call this convection. So if I were to come over here and heat the air up really hot right here, so it was like 1,000 degrees, even if I didn't blow a fan, what's going to happen to the air in this room? It's going to rise up, but it's also that heat is going to spread out because every particle here is going to be bouncing around like crazy. It'll hit the particles next to them. So heat will tend to disperse. We call that convection. All right? Which also means that gases tend to spread out. What do we call that? Liquids do this too, but here we're talking about gases. Gases spread out. What do we call that? Science term. We talked about it a lot in biology, if you took biology with me. Diffusion, right? If I am a grade 9 boy, and I have recently discovered that I stink, as hopefully every grade 9 boy eventually discovers, I then discovered that there's only one way to solve this problem. And you might think, yes, regular showering and use of soap. But no, the answer, of course, is Axe body spray. Lots of Axe body spray. So much Axe body spray or some other god-awful cologne. But if I cover myself in gaseous Axe body spray, does it stay with me? Oh no. it spreads out, right? Because each of those particles bounces into each other, and left with enough time, Einstein actually wrote a paper about this in 1913, 12. Is that his Annus Mirabilis? He has this year where he writes 4 major papers, one of which is about Brownian motion, which describes the physics of how particles that move randomly, weirdly enough, don't end up moving in random directions. Randomly moving particles end up moving to spread out. And you'd think that's a little weird. You'd think if you move in random directions, wouldn't it sometimes happen that you move over here and sometimes happen that you move over there? But Einstein's, this is like his cheap American counterpart. Einstein's paper on Brownian motion shows us that actually if you do the physics, it shows that particles moving in random directions and colliding with each other will eventually spread out evenly. In the long term, in the short term, they can actually do interesting things, but in the long term, they will spread out. So those are collisions. But then we also get what we call pressure. Gas particles collide with their surroundings. And we call this force of collision pressure. That can't be right. Collision 2S, that's not right. We call the force of, guys, collision, talk to me. C-O-L. Pass it on. Pass it on. Start the chain. Cooper, don't let me down. There we go. Okay. C-O-L. Is that right? Why does that look so wrong to me? Is it? But that looks terrible, right? I hate that word now. I'm never going to use it again. It's out of my lexicon. Never again. I hate it. That looks terrible. All right. We call the force of gas particles colliding against other things pressure. I got to say, Heimple, you made that hard. But listen, we're a team. I got to say, team 2, that did not happen quickly. I got through several incoherent ramblings in the time it took that paper to transition 1, 2, 3, 4, 5, 6 people. I'm just saying, we can do better. Anyway, let's focus. Pressure. Now, pressure is such an important thing that we've been measuring it for a long time, which is a good thing because it's important, and it's a bad thing because there's a bunch of units for doing so. So we'll talk about 3 of them. In fact, we might even talk about 4 because we should talk about pounds per square inch, right? Because that's also really intuitive, right? And actually, pounds per square inch is what makes you realize just how strong gas pressure is. Like we said, it's weird to think about because you're just so used to it and you've never lived without it. I thought you were reaching for that Axe body spray. I was like, oh, here we go. He heard me. He's like, oh. There's a law. There's a fundamental law of the universe which says that the particular time and place that every grade 9 boy discovers their love of Axe body spray is right outside my classroom. I swear to God, there's like 4 or 5 days a year I come in here and it's like, whoa, wow, holy Lord, what's going on? But again, diffusion. By the end of the day, just spreads on out. Anyway, when we measure pressure, we have a bunch of units. The first one is also by far the worst. In America, they still measure pressure in torr, or millimeters of mercury. Now, that's especially ironic, given that the Americans don't measure distances in millimeters. What the hell does that mean? Anyone? Anyone? Okay. This is actually how you measure pressure. We have all kinds of ways now, but the traditional way you measure pressure is you use a barometer. Has anyone heard of that before? A barometer. You may hear about the barometric pressure. You don't have to draw this, all right? Don't draw this. But here's how a barometer works. If you take a cup and you put some liquid in it, And then you take a glass tube that is in a vacuum. Do you know what I mean by a vacuum? There's nothing in it. No gas, no air, no anything. So if you take a vacuum tube and you put it here, all right? Because it is a vacuum, what's it going to do to that liquid? It's going to suck it up. But it can't suck it up forever. It can only suck it up until the pressure balances out. Does that make sense? So it will suck the liquid up into the tube by way of pressure. So here's the thing. If you take a beaker of water or a beaker of alcohol and you do that, the vacuum tube will actually suck it up for like many feet. I'm trying to remember what the limit is, but it's high. It's like you can suck water up a tube for like 15 meters maybe under normal atmospheric pressure. So that's a bad way to measure this. Does that make sense? You'd have to have this really tall, big glass tube. You can test this, by the way. Get the longest straw you could possibly find, put them together, make sure they're airtight. Try it. Could you use a straw to drink from a cup from the second floor if the cup's down on the ground out there through the window? Try it out. See how high you can go. We did this in high school as a physics project one day. We had my friend go down, and we staged it so it was like we were stealing from him. He actually knew, but right. And then we reached this really long straw down from the second floor and drank his pop, right? So the problem with measuring pressure that way is bad. But you want to know what a liquid that is really heavy is? And so it's hard to suck up a straw? Mercury. Mercury is really heavy. It's a heavy liquid. It's the heaviest natural liquid. So what you do is you fill a little container with mercury, and then you put this tube here. Because in the end, why does a vacuum suck the mercury up? Well, the vacuum sucks the mercury up because the air is pushing down on the mercury. And if there's no air in here pushing down on the mercury, then what does the mercury do? Air pushes it down here. Nothing is pushing it down in the tube, so it moves up the tube. And the higher the pressure, the higher the mercury will move up. Does that make sense? This is not like a thermometer. That's an entirely different principle. That's a sealed tube. This isn't sealed. The air can come in here and push on it. Does that make sense? And so what is going to determine how high the mercury will rise in the vacuum tube is the air pressure. Does that make sense? Higher air pressure, the mercury will move up. Low air pressure, the mercury will move down. Does that make sense? This is a barometer, sometimes also called a manometer, all right? But a barometer. And so if you build a barometer, the higher the mercury goes, the more the pressure. And so we measure in millimeters of mercury pressure. And the pressure in this room right now, this is the one I can never remember. So you guys are going to have to forgive me. I'm just going to have to Google it because we do not normally use this as a unit of measurement. Atmospheric pressure in millimeters of mercury. 760 millimeters of mercury. So 76 centimeters. So if you ever see a real barometer, they're still tall. It's like a meter stick. Do you know what I mean? Like 760 millimeters is 76 centimeters, right? Or almost a meter. So this is still not only going up a bit. Even mercury, which is a very heavy liquid, air pressure can push it up almost a meter. What's the maximum height? Maximum height of suction for water at atmospheric pressure. I think it's in meters. Yeah, like 34 feet, 10.3 meters. So you could be 10.3 meters above your friend and steal their milkshake. Well, actually, milkshake would be heavier. Forget that. You probably can't steal their milkshake 10 meters up, but you can steal their bottled water 10 meters up. I challenge you to do that to somebody this week. Make yourself a 10-meter long straw, go to the second floor, steal somebody's drink. Maybe down a stairwell. Wouldn't that be cool? You know those kids who always sit here in this stairwell and are really noisy at lunch? Wouldn't it be fun to steal their soda? Build yourself a 10-meter long straw. That's what I want to see. But you can only suck mercury up 760 millimeters of mercury. So normal atmospheric pressure is 760 millimeters of mercury, which we write as mmHg, or we just sometimes call that torr. Do not ask me what that means, but I think it's a guy's name because it's an uppercase T. And when science units have uppercase letters, they're usually people's names. Crappy unit, right? But it comes from a physical property. The SI unit, in other words, the international unit, the unit we use in chemistry, is the Pascal, or specifically the kilopascal, 1,000 pascals. Does anyone know what ambient atmospheric pressure is in kilopascals? The pressure in this room right now, probably. It goes up a bit, sometimes it goes down a bit, sometimes. But the global average, 101.3 kilopascals. So kilopascals are the standard unit of pressure. These are nice because they convert easily to joules and to grams. Like, this is what you want to actually, this has a definition. In fact, specifically, the definition of a Pascal, the SI definition of the Pascal is 1 Newton per square meter. Does that make sense? So a kilopascal is 1,000 newtons of force for every square meter. So we'll mention that. A kilopascal is 1,000 newtons of force on every square meter. You don't have to worry about that if you're not a physicist. But again, if you are in physics class, you know what a Newton is, right? If you think about it, that's a lot more force. For example, I weigh, depending on the week, let's say about 100 kilograms, right? Give or take. Does that make sense? And gravity pulls down on me with a force, an acceleration, as you know, of 10 meters per second squared, 9.8 meters per second squared, but we'll round that to 10, right? Which means that I put roughly 1,000 newtons of force. So look at me. I want you to think about this for a second. I put about 1,000 newtons of force when I stand on the ground, which means that the air is pushing on you with the same amount of force as if we got a 1 meter square piece of wood, put that on top of your chest, and then I stood on that. That probably wouldn't feel good, right? I'm assuming. That is how hard the air is pushing on that part of your chest right now. But you don't feel it because your body is designed to push that same amount of force out. That's weird to think about, right? So air is not some little force. Every square meter in this room is being pushed on with the weight of me standing on it by air. Weird, right? Weird. Now, because that number is kind of ugly, it's actually not that ugly. It's kind of just 100, basically, right? If to 2 sig figs, standard air pressure is 100 kilopascals. That's kind of nice, right? Because it's 100 kilopascals, pardon me, every square meter is, getting 100 of those. So it's like being stepped on by 100 of me. Again, air pressure is serious business. We're just used to it. It's a balanced force. We also have gases inside our body that push out just as much as the gases outside our body push in, right? Weird stuff. But because that's not a nice number, sometimes, to make life easy, we just say, let's work in a unit, a blessed unit, a wonderful unit called atmospheres. And you know what the definition of that is? We just say 1.000 all the way to infinity. In other words, exactly 1 atmosphere. But I'm going to match it to sig figs for this. 101.3 kilopascals is 1.000 atmospheres. Does that make sense? In other words, somebody had the bright idea to say, well, since this is the number we're going to have to use over and over again, why don't we just set it to 1? I actually don't like atmospheres. Kilopascals is the unit we should be using because it converts to other things. It's nice. And then the last one we'll see is pounds per square inch. And then again, I want to get that number exactly. So let's convert 101.3 kilopascals to PSI, and it's 14.69. 14.69. And again, I just want to stress that every single square inch of your body is being pressed on by 15 pounds of pressure right now. Top of your head is probably a good, 20 square inches, which means there's 300 pounds of air pushing on your head right now. Weird, right? Weird. In my case, all the hot air inside my head pushes back with equal pressure. Perfect balance, not an issue. Okay, how's that feel? Not too bad? Okay. I want to note this is a conversion table right here. You can use any of these values combined to convert using dimensional analysis. Does that make sense? Because we're saying these are all the same. This is the atmospheric. So this is your conversion table. For units of pressure. So for example, let's say that we looked and we saw that my tires, the tires in your car have to be compressed. Do you know what a typical tire compression is? You can check the side of your door. If you open your door, there'll be a little sticker there that has to be by law in Canada. It tells you what pressure you should inflate your tires to. Anyone know what car tires typically are inflated to? Depends on the tire. You won't see lower than 35, and you won't see higher than, say, 45. 38 to 41 is like a standard range. What about bike tires? Anyone here a cyclist? A little bit higher, typically about 80. Some as high as like 100, 110. Some as low as like 60 on a mountain bike, but that's your range. So let's say that my car right now, my car recommends inflating your tires to 38 pounds per square inch. 42, you get a rougher ride, but you get way better gas mileage. So I keep my tires at 42 pounds per square inch. That's what I've found to be the best balance of bumpiness of ride to fuel economy. And if you're wondering, did I make a spreadsheet and slowly change it by values of 0.5 over a series of weeks and then take measurements of my fuel economy? Yes, I did. So the tire pressure of 42.5 kilopascal or pounds per square inch that I keep my car at, what is that in kilopascals? What would we do if I want kilopascals instead? Just to make sure we understand how you can convert this table. Because we know all those values are the same. So we'd just do a little dimensional analysis and we'd say, what don't I want to talk about? Pounds per square inch, right? So I don't want PSI. What do I want instead? I want kilopascals. The kilopascals, however you want to pronounce it. And what do we know about this relationship? Well, from this table, we know that 101.3 kilopascals is 14.69 psi. Can someone do that math for me, please? That should be 4,200 divided by 14. So like, that's going to be just shy of 300. Yeah, just shy. 293. And I'm in 3 sig fig land, so 290. Does it round to 3 to 4 or stay at 3? Oh, perfect. So 293 kilopascals. And in fact, annoyingly, the tire pressure sensor system in my car, I have my new car. This is new for me. It's got the thing where like it tells you what the tire pressure in all 4 of your tires is. That's cool, right? Like up on the screen. That's fun. See that? But it's in kilopascals because we're metric, but of course we inflate our tires in PSI. So, I actually know that I like to set mine to 293 kilopascals. That's my target. By the way, you'll see that changes for a variety of things. But there we go. And when you think about it, it's weird, but that is enough pressure that the entire weight of your car doesn't squeeze those tires down, right? And you can see, like, even watch your tires sometimes. Get like the 3 heaviest of your friends to get in your car and watch your tires. They don't squeeze, right? Like that is so much pressure because again, each kilopascal is putting 1,000 newtons of force. In other words, my weight of force. Each kilopascal is doing that on, your tires are probably basically a square meter. So you're talking about like 293 times my weight acting on the surface of those tires. And that's why somebody can get in your car and they don't push down or deflate. Air pressure is an incredible amount of energy. Does that make sense? All right. So now we know that the reason that gases put force on things, the reason there is pressure is because gas particles are moving and they hit stuff. But of course, how hard they hit things, how much pressure they provide is going to depend obviously on how many particles there are, right? More particles, more collisions. But it's also going to depend on how fast they're going, right? You put a lot more pressure on something when you hit it with a fast-moving object than when you hit it with a slow-moving object. In fact, you know that the speed is more important than the mass. What's the formula for kinetic energy? Physics students, don't worry about this if you're not a physics student. The kinetic energy of an object in motion is measured as what? EK equals 1/2 mv squared, right? So the velocity at which an object is moving is by far the most important factor in how much energy it has and how much force it's going to provide, right? So, again, if you're not in physics, don't worry about that. I'm just helping these guys study for the final. So, when we're talking about gases, how do we measure how fast they're moving? Not in meters per second. We measure it in what? What'd you say? Is Newton's a measure of speed? No, of course not. Newton's a measure of force. We can't really measure particles in meters per second or whatever because they never get to travel a distance long at all. Does that make sense? If you're a gas, you're not going from here to the window because between here and the window is an infinite number practically of particles. You're bouncing all over the damn place. Does that make sense? So you can't really measure their speed by taking distance and time because they're constantly bouncing around. We measure their speed by calling it their temperature. Temperature is a measure of the average kinetic energy of a gas particle. So it's not quite speed, it's kinetic energy, but that's related to speed. So temperature is a measurement of the average kinetic energy of a gas particle. And we're going to write this, EK equals 1/2 mv squared. And we're going to say that primarily what we're measuring is speed. V is velocity. So we can say for a gas where all the particles have the same mass, does that make sense? So if you're talking about oxygen mass, every oxygen atom has the same mass. Therefore, its temperature only depends, its mass isn't changing. So its temperature depends on its velocity. So a gas's temperature depends on how fast the particles are moving because a gas's mass doesn't change. I mean, except it totally does at relativistic levels, but you do not need to know that at this level. So the purpose we understand, the velocity determines the temperature. So when we are turning the temperature up on a gas, what we are doing is making the particles move faster. And when we turn the temperature down on a gas, we are making the particles move slower. Does that feel comfortable? Okay, now we have a problem. We typically measure temperature using what unit? Okay, we typically measure temperature in 2 units, right? Fahrenheit and Celsius. In Celsius or Fahrenheit. Does anyone know where the numbers come from? Celsius, you probably, almost certainly you do know. What is 0 Celsius? What is 0 Celsius? Yeah, it is so chosen because it is the freezing point of water. Why did they choose that? Okay, sure, yeah, but why make that 0? The answer is a practical one. If you want to build a thermometer, you take a glass tube, you put some alcohol in it. Alcohol is a good thing to choose because it will not freeze. You could make a thermometer with water. The problem is your thermometer will definitely stop working at 0 degrees Celsius, right? Does that make sense? So we don't do that. So you take a bit of, you do a vacuum tube again, but this one you seal. You put some alcohol in there, you dye it red so that you can see it. And then you got to put lines on it, right? You got to put numbers on it. Well, how the hell do you know where to put the lines? Well, Celsius had the bright idea, okay, well, let's just take a bucket of water and fill it with ice. if you mix ice and water and leave it for a few minutes and stir it, what temperature is that ice water? Has to be, if it's pure water. What temperature does it have to go to? Exactly. Eventually, all things, if you put two things against each other, they will become the same temperature, right? You know this. If you put your hand against a cold piece of metal, leave it there for a minute, the metal becomes the same pace as your hand. As anyone knows, when you're overheating in bed, you flip the pillow, it's nice and cool for like 12 seconds, and then the heat of your head warms it, and now it's warm again, right? So, if you mix ice, what's the hottest ice can be? 0. And water, what's the coldest water can be? 0. You mix them together, what temperature will it be? It's got to go to 0. So if you're building your thermometer, make your glass tube, you put your liquid in it, and you seal the top so you get a flame. Sometimes in the past, I've actually done this as a lab. We just built thermometers. We just get some glass tubing, we heat it up on a Bunsen burner and close one end, we pour some alcohol in. We don't use alcohol, we use water, because alcohol is flammable. So we've made shitty thermometers, but still. And then you take the other end, and you heat it up with a torch, and you close it. Now you have a sealed container, right? And then, to mark your lines, you put it in ice water. Wherever the thermometer stops, you mark a line there, and you call that 0. Then, where do you put it next? So you can mark a line at 100. What's 100 Celsius? It's the boiling point of water. This is actually a really practical thing, because see how easy it is to make a Celsius thermometer? You put it in ice water, you mark a line, then you put it in boiling water, you mark a line there, it's going to go up, you mark a line there, and then if you just divide that by 10, now you're going up by 10s, and if you divide each one of those by 10 into 10 slashes, now you're going up by 1. Does that make sense? So Celsius is a practical scale. It is made so that you can make thermometers quickly, cheaply, and effectively. It's pretty smart. Fahrenheit, well, actually, Celsius, to get that 0 degree thing, you have to get pure water. If your water, tap water, will actually get a little bit below 0. Because when you dissolve minerals in water, when you have an aqueous solution, most of those things actually bring the melting point of water down. Which means that if you don't have pure water, and you do this with tap water, your 0 will be a little bit too low. And if you say use brine, like really salty water, it'll be really low. You've seen this because like a freezy can still be slushy in the freezer at a temperature that like pure water would be an ice cube, because it's got all kinds of stuff dissolved in it. So Fahrenheit said, we're going to set 0 at, does anyone know? This is the melting point, or the freezing point, of saturated brine. In other words, if you put as much salt. So he said, you don't need to get pure water. Let's actually do the opposite. Let's get water, and let's just fill it with salt till it won't take any more salt. And then let's take that to its freezing point. So the freezing point of saturated brine is 0 Fahrenheit. And then there's some debate over this. But 100 Fahrenheit is roughly body temperature, but it's a screw up. What is body temperature actually in Fahrenheit? Does anyone know what's your body temperature in Fahrenheit? 98.5 degrees standard. Like 97 to 99 is standard. If you have 100 degrees, you have a fever. But that's apparently where 100 comes from. What's body temperature in Celsius? Team, you should know how your bodies work. What's body temperature in Celsius? Your core organs. No, you'd be dying of hypothermia. I think, so roughly 35. I believe the healthy range is as high as 36.5. This is why I need my wife, but it's a small range. It is, yeah, like 36.5 is considered standard, but what is the, Cleveland Clinic, that'd be good. Cleveland Clinic is a good site for, yeah, 36.6 is the standard. But yeah, 35.5 to 37.5 is typical, is healthy. If you're just a couple of degrees above that, you have a fever and you could die. If you're just a couple degrees below that, you have, what do we call it when you have too low a body temperature? Sorry? Hypo. Hypo, too low, thermia, thermos, heat, too low heat, hypothermia. Hypothermia will kill you. Your fingers can get quite a bit colder than that. Your toes can get quite a bit colder than that, though they will eventually fall off. But your core body temperature, the proteins that make all those things work, your brain, your heart, your liver, your spleen, your kidneys, they have about a 3-degree temperature range they work well in. And anything outside of that, you are dying, literally. So scary. The body not, and that's for humans. Other animals have very different adaptations, but humans, very sensitive to temperature change. What's the problem with both of these scales? We just said temperature is a measurement of what? Average kinetic energy. Does 0 degrees Celsius water, does frozen water have no kinetic energy? Are those particles still? No. In fact, in grade 9, we learned that all particles, even solids, are constantly in motion. So here's the major problem with these. These units cannot be used. You can't do math with them. You cannot multiply or divide ever. Look at me. You cannot multiply or divide by Celsius or Fahrenheit because the act of multiplying and dividing is rested on the assumption that 0 means 0. Right? Look at this is a key thing because when you convert one unit to another, 0 is still must be 0. Do you know what I mean? Meters and inches, very different, right? But is 0 meters the same as 0 inches? Well, those were the two options. Which one is it? Yeah, if something is 0 meters long, how many inches is it? 0, right? That's true in any unit. If you have 0 ounces of wine in your glass, because you drank it all because one of your students suggested that 0 inches isn't the same as 0 meters, do you have 0 milliliters of wine in your glass? Well, of course. 0 is 0, right? 0 has to mean 0 for you to be able to multiply by a unit. You can still add and subtract if you make up stupid fake units. But listen, Celsius is like this. Everyone stand up. Celsius, and guys, if this is like, listen, if I'm going to get written up for this, I pre-apologize. But who's the tallest person in this room? Who do we think? Probably you? How tall are you? Wrong, you're 0. From now on, we are defining 0 as how tall this guy is. All right? Is that cool? He's 0. He is 0 feet tall. Can I do that? Sure, I can do whatever I want. I'm a teacher. Problem with that is you're what, 6'1"? Now we got, okay, my height now, because we've just called his height 0, is negative 3 inches, maybe 4. Can we do that? Sure, will it work? As long as we're adding and subtracting, that'll still work. I bet I'm a little taller than you. What are you, like 5'7"?
I think, yeah.
Yeah, and I'm about 5'9". So I'm about 2 inches taller than you, right? Well, in this new system, if you're 5'7", you're negative 6 inches tall, right? We said I'm negative 4 inches tall. Am I still 2 inches taller than him? Yeah, of course. Except if we try to multiply or divide, it all breaks. Because now, according to that, I'm twice as tall as him. Am I twice as tall as him? No, because multiplying, you can all sit down now. Multiplying and dividing only works when 0 actually means 0. Does that make sense? For adding and subtracting, you can pick a point and call it 0, and that's fine. You can define 0 as anything you want. And usually when we work with temperatures, we're just adding and subtracting. We don't care how many times hotter it is out, though you'll see people say things like this, you know? Like if you think about it, like if you heat your oven up from 200 degrees from 400 degrees, in your head you're like, oh, it's twice as hot. But it's not twice as hot. Do you know what I mean? Because if your oven were set to 0, in other words, if your oven were a freezer, 0 doesn't actually mean 0. Do you know what I'm saying? 0 happens to be the number where water turns to ice, but it's not no temperature. It's not no kinetic energy. Does that make sense? So we cannot use degrees Celsius or degrees Fahrenheit to multiply or divide because their 0 value is not a true 0. So what would be a true 0? Hi, I'm sorry, I'm ignoring you. This is lovely, by the way. When did that happen?
Yesterday.
Who did that?
I did.
You did that. Oh my God, can I see that? That is very impressive. What can you for?
I just want to say I got the family scholarship.
Oh my God, did you actually?
Yes.
Congratulations.
I got the news by mail on Tuesday.
Oh, I am so... Okay, we'll talk later. I am so overjoyed. Congratulations.
Thank you.
That is fantastic. Wow. Oh, that's amazing. Sorry. What would it mean to actually have a temperature of 0 based on our definition? We said temperature is really just the mass of the particle, which obviously doesn't change, times its velocity squared. For the temperature to be 0, what would have to be 0 then? Either the mass of the particle. Can an object ever have a mass of 0? By definition, matter has mass, right? Okay, so a mass of 0 can't happen. So how can you make the temperature? How can you make the kinetic energy be 0? What would have to be 0? The velocity would have to be 0. So the true definition of absolute 0 is the temperature at which particles stopped moving. Now here's the problem. We live in a universe where energy has to be conserved, which means that is impossible. Not hard to do, not difficult. Our science tells us that that should be impossible. Does that make sense? So true 0 temperature. Yep. What I mean by energy has to be conserved is that all of the energy in the universe cannot be created or destroyed. That is the first law of thermodynamics, right? Energy cannot be created or destroyed. It can only be transferred from one thing to another. Does that make sense? But the way energy gets transferred by movement is by things bumping into each other. Does that make sense? But because particles are always bumping into each other, in theory, could the velocity of a single particle go down to 0? I guess if it managed to bump into something, as this happens sometimes, maybe you've taken a pool shot in your life where the shot ball just stops and the other one goes. Okay, so the kinetic energy of a particle could potentially go to 0 for a time until it interacted with something. But can the average ever go to 0? Because if we start out with this one not moving and this one moving, and the average is, say, 5 kilometers an hour, because this one's going at 10 and this one's going at 0, if we hit it such that this one is now going 10 and this one's going 5, what's the average now? 5. Does that make sense? You can't ever have the average go to 0 if the energy isn't disappearing. Does that make sense? Some particles can stop, but the only way some particles can stop is if other particles speed up. And again, particles, there's not 3 of them. There's trillions. So at any given moment, some might be stopped because it's really cold, but they're going to get moving again because the ones around them are moving. Matter can never come to a stop. Again, it's not hard to make it come to a stop. It can't happen. It might be able to happen for a single particle. That's something particle theorists are playing with, but it cannot happen for a meaningful mass, for a serious, in theory, even 2 particles, right? If one stops moving, the other is going to start moving. And anything that can only happen to one particle has no practical meaning in a world where everything is made of countless numbers of particles. So absolute true 0 temperature would be when the average speed of a particle is 0. Since EK equals 1/2 mv squared, the velocity would need to be 0. This is impossible. We call this absolute 0. And it's not possible to reach and maintain absolute 0. We can get incredibly close. And in fact, we have the math available to us that we can calculate what absolute 0 would be. Does that make sense? You can do the math. You can just set v to 0. in EK equals 1/2 mv squared. You can work it all out. So absolute zero would occur at negative 273.15 degrees Celsius. Turns out that's how cold you would have to get something for it to really be zero. So Celsius is a bad measurement of temperature. And it really is. We should just stop using Celsius altogether. It shouldn't exist. And we should stop using Fahrenheit altogether. And in fact, in science, we basically have. We don't talk in terms of Celsius. We don't talk in terms of Fahrenheit because it is bad habit to work with math where zero doesn't mean zero. It would be stupid if all of us in this room decided from now on that 6.1 you said? If we all decided that 6.1 was zero. You know what I mean? That'd be a bad decision. That makes life hard to talk about, right? So we call this 0 Kelvin. Not degrees Kelvin, just Kelvin. But to make life easier for Celsius people, the Kelvin temperature scale starts at 0, but a change of 1 degree Kelvin, or of 1 Kelvin, is the same as a change of 1 degree Celsius. Okay, so look at me. This is a little weird at first, but I want to make sure you get it. That means that Celsius and Kelvin go by the tick marks. If you made a Celsius thermometer and a Kelvin thermometer, the tick marks would be in the exact same spots. You know what I mean? It's not like centimeters and inches where the tick marks are different sizes. It's just instead of marking 0 on the Celsius when ice melts, we'd actually mark that at 273.15 because 0 would be 273.15 below that. But all the tick ups would be the same. Does that make sense? With 3 sig figs, 0 Celsius is 273 Kelvin. So if you're making your thermometer in Kelvin, you'd put it in ice water and you'd mark that as 273. And then you'd put it in boiling water, and instead of marking it at 100, you'd mark it at 100 more than 273, which would be 373. Does that make sense? So in Kelvin, in this room right now, it's about 293 Kelvin. That's about room temperature. Actually, this school tends to run a bit hot. It's probably maybe 295, 296 Kelvin. Does that make sense? Same scale as Celsius. So here's how it works. To convert, the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. Now, we could go to more decimal places than that. This gives us 5 sig figs. That's going to be plenty for anything we do in this course. Does that make sense? You could go to a lot more sig figs than that. And that would mean that the temperature in Celsius would just be what? How do you go the other way? Yep. Temperature in Kelvin minus 273.15. Now, I suppose we ought to mention the other stupid system because it does come up sometimes. If you want to know the temperature in Kelvin from the temperature in Fahrenheit, it's not just going to be adding or subtracting. It's also going to be multiplying and dividing. But it's a linear relationship. So if we are converting Fahrenheit to Kelvin, don't, listen, see this? Don't assume that you can just multiply by that, because this is actually a non, what do we call linear relationship that doesn't go through 0? I'm not asking to be like a coy teacher. Those indirect, that's the word. This is an indirect relationship. You have to multiply and add or subtract. Does that make sense? So the equation is, it's brutal. The temperature in Kelvin is the temperature in Fahrenheit plus 459.67 times 5 over 9. That sucks, right? Can we all agree? Don't use Fahrenheit. Fahrenheit sucks. But if you want to know the temperature in Kelvin and you're given the temperature in Fahrenheit, you can do that. And I will certainly never ask you to convert the other way and give me a temperature in Fahrenheit, because Fahrenheit is stupid, all right? I mean, Celsius is stupid too, but Kelvin is good. We like Kelvin. But if you are ever given a temperature in Fahrenheit, there it is. Is that cool? In chemistry, we have never converted units by adding or subtracting, right? Look at me. So you actually can't do dimensional analysis with this because dimensional analysis assumes ratios. Ratios assume that you can multiply and divide, and multiplying and dividing assumes that 0 means 0. But Fahrenheit and Celsius are broken. They are broken units. They do not work. Qu'est-ce que c'est?
This was plugged in my room because Nalini uses it for
5. Can I have it back?
But
you don't need it.
No,
you
because
don't.
I wireless.
Hallelujah! I step back.
Yeah.
Thank you.
So I didn't know if it was yours.
It is mine. Yeah.
Okay.
Yeah, that's great.
I figured I'd come here first, and then Candace and I are both moved.
Oh wow! Oh,
Yeah.
oh, and I didn't even help. I feel bad.
Whatever, our kids did it all.
That's amazing.
Yeah, my kids moved me completely. Tanya just moved my desk, and then
They're just using the science office for storage now, by the way. So I sent an email to Josh yesterday. And
Candace said something to Josh on.
But I
Tuesday.
just sent another one and said, like, they are just using it to store the stuff. They are also storing a bunch of stuff in the whiteboard room. Can they please move all that stuff to the whiteboard room?
Just move it to the paper room.
If
no one's moving in there anyways,
and if they, I see they have a couple ceiling tiles down. If they're gonna have to go on the ceiling tiles a couple more times, who cares? I'm not looking to fill the center. I just want to get stuff in there. Like they can shimmy our stuff and put a ladder up anytime they need to go on the ceiling. I'm not gonna put anything in there they can't get a little dusty. I just need in that room.
Yeah.
Like enough's enough. I can't live like this anymore. I can't do it.
Which is a lot coming from you.
No, I can't.
No, but I mean, which is a lot.
I can handle chaos. I can't handle this much. Guys, I want these conversions done. Go.
Yeah,
Go,
no,
convert.
the kids
Convert.
moved us,
Make it happen.
My kids helped moved Candace's desk, and they moved there, and then Tanya
Amazing.
moved her desk from upstairs to downstairs.
That's awesome.
And we're done.
That's awesome.
She was going to move period 3, but then her kids were just moving, so
Why?
she might as well.
So everyone's home.
Everyone's home.
Everyone's home. You're semi-home.
Semi-home.
I mean, your room kind of sucks. I hate it.
Should we do that? Because when you find it done, I don't ask any question.
Are we converting? Are we converting? Excellent. When you think you've got one, come put it up here.
Typing in your calculator and then writing down the answer.
Okay, I would rather. Yeah,
What are you doing?
that makes sense now.
Are you not doing the same? Oh, you're actually putting like that. Oh, that's one second.
Nobody's put one up? What are you guys doing? Come on, you got 1 minute. I want these filled in. Thank you for showing your work.
Do I have to show them?
I mean, sure, that's okay. But listen, he at least stepped up and did it. Also, thank you for zooming out. Because I always find like the opposite. I want to zoom in so I don't have to try to write really small on it. That's interesting. That's actually, by the way, really neat. To have written that small, I struggle to write neatly on that. Guys, good job getting that filled out.
Sure.
Is what I'd be saying if you hadn't shot the bed completely and not gotten it filled out, which you did. You had one job, Jim.
Oh no, I'm not gonna be able to write that
This is
small.
crochet. This is crochet, right? That's all the time. She does my crochet. And all right, but I like flowers, but I never get plants.
Just zoom in.
I just can't. I lack the. What do I lack? I feel like I lack plant empathy. I think that's the real problem. I feel like in the end, like good gardeners actually empathize with the plants. Yeah, right. And I just don't have that.
You ready for the physics
By the
test
time I
next
realize
period?
there's a problem, I always seem to
Uncle,
overcompensate by giving it a
did you
lot
study
more.
at all?
And it turns out that's
Do I
not the
believe
thing
you?
No.
So,
Should I believe you?
I'm bad with plants.
Is studying
I'm totally fine
more
with
than
that.
2
Yeah,
minutes?
that's great.
Yeah.
Yeah, no
More
problem.
than 5?
Yes.
If I have forgotten
Did you
them across
watch
the
more
hall,
videos?
which, by the way, I was. So
you're
maybe
good.
across the hall, almost certainly it's coming up.
Do you want to write one too? You got that? Oh, I love how neat my handwriting is.
And then, like, cheat by studying all the stuff.
It does not look like a 9. Should we punish them for not writing by me writing all of them?
Yeah.
You know what? That's not bad. That's not bad at all.
Stop. Write the rest, but don't try as hard.
Alright,
You do
alright.
better. You do better. Let's.
Yeah, you can do
That's
better.
not all smart.
You can do better.
You do better.
Okay.
You can do better than me.
Orlando,
Yeah.
need your period 1, please.
Yeah. F word. F word. I'm about to say the thing.
How do I undo that?
Come on, Cooper, you have that.
Okay, I don't got better.
You can write. Why are you writing like me?
I don't got better.
Why are you writing like me?
Ah,
I would say swim the rock, but no. Cooper, yeah.
I don't got this.
Cooper, why are you writing like me?
I don't got this.
Alright, fine.
You got that. I don't got it.
Don't forget, we have a
Oh wait, I didn't know I didn't have to. Oh, then I got that.
No, you got that. What are you doing? What were you doing?
I was writing like this because I thought if I touched it with my hand.
Why were you doing that?
Minus
Hey,
270.
you lock in.
Which equals to negative. Which equals to.
271.25.
See, I got better.
Alright, I'll write the rest just to punish them.
273.15. Read it aloud, Okay, so you were also writing. You were also writing like I was trying to, with not putting any of your hand on the screen.
Sorry.
And by that, it's just temperature in the Wait, why am I putting my pencil? What am I doing? No. Okay, cool. He just has to make an aspiration value. Yeah. He asked me once for a minute, and I'm just like, aspiration value. Did you win the first one, or did you lose slightly worse? You know, it's not that bad. You gotta make the last one so unreadable. Like, just make your answer really unreadable.
Yeah, but I mean, to be fair, we can try hard, bro. We all play baseball.
Maybe we should get you writing on this full time.
They were throwing out at least 18 feet. There was no way.
How do you write on one of these full time? Handwriting's better.
Oh, that does not look as good as it does on the screen.
This one's bad. This one's bad.
It's readable.
Just the 7 on that one's really bad.
Better.
Do you normally write your 7s like that? Or are you just doing
the
it
line
to
in the middle?
appease him?
With the line in the middle, yes.
Why do you do that? That's not what the 7 looks
Oh
like.
my, that looks like a T.
Do you want me to do it?
No.
You got this.
I'm punishing students for...
Here, I don't really need to.
There. I always write my 7s with a line in the middle. I used to not, and then I was like, I kind of like writing a... I kind of like drawing a line, so let me just do it.
Where's the line?
Yeah, on the calculator it's not. Most 7s don't. I just do. I used to not, but...
You could go back.
Why is my handwriting so bad? God damn. I can guarantee it's not. It is. Why is it so big? Yo, should I just do the... Should I just print it?
There, I fixed that. I changed it from looking like a 4. I fixed your 9 in the first one.
Right, tried fixing it before. Oh, how does he do the one tool? The
What?
this.
What? Highlight it?
Oh,
Circle it.
and then we're gonna just.
Make it really large. Just make it really large.
No, I want it smaller.
No, it's fine. Leave it. Don't shrink it. Why are you making it worse?
Because they're too big.
They're normal. They're fine.
All right,
No,
team.
whatever.
I often think about when I was in grade 10, we were in history, and one day my teacher, Mr. Clark, put that away. You're doing which? Ah, of course you.
You might want to rewrite things.
No, they look lovely. You guys did a lovely job. When I was in grade 11, or grade 10, history teacher, Merv Clausen, he was an interesting fellow. Not I wouldn't say a wonderful teacher, but a competent teacher and a nice guy. But one day he came into class and he said, "All right, guys, you don't like me." And I thought, "I like you. You're fine." He said, "No, I don't like you." And I thought, well, that's news to me. So here's what we're going to do. I'm going to sit. I'm going to read this newspaper. And you're going to be silent. And he proceeded to sit and open his newspaper. I think after about 3 minutes, like my friend Jesse turned to like Michael next to him and was like, "Hey, can I have a pencil?" And he went, "Did somebody not understand what I meant by silent?" And then he'd proceed to continue reading his newspaper, and we continued to sit in silence for remaining 72 minutes. And I think about that sometimes. That's all. It's the end of my story. And a good story it was. Today, we want to carry on talking about sequences. Now, you have already looked at arithmetic, a word that I find it impossible to say, but arithmetic sequences. And this, of course, is like a linear relationship, right? In fact, when you first learn this stuff, you could be forgiven for thinking, isn't this just a line? And then yesterday you learned about geometric sequences, right? Or geometric series. And again, you could be excused for thinking, isn't this just an exponential function, right? Yes. Yeah, you guys weren't here yesterday. Pardon me. I apologize. On Tuesday, you learned about geometric sequences. And again, you could be pardoned for thinking, isn't this just exponential growth? And we give you this definition of difference, right? Which is we say, yeah, but the difference is, right? The difference is that sequences are discrete. What do we mean when we say that sequences are discrete?